All right, so here we are in the classroom once again. The semester is drawing pretty close to a close. We only go through 15, and you can see that this is class 11. So it's April. We're getting close to the end. Let me just make the announcement about the presentations that you're going to do next week. It's actually a week from now. As a reminder, those should be between 20 and 25 minutes, should include a calculation example, and you should email your PowerPoint file to me at least 2 hours before class. Here's the list of who's doing what. One thing I'll point out is that one of our students dropped the course, and so Song and Malati, you'll do your topic together, but that third student isn't in the class anymore. It kind of worked out coincidentally that was the only group that had 3 students. So I'm going to ask you to actually work your example today. I've got a pretty lengthy, detailed in-class exercise for you. And so I'll ask you to work in these pairings for that example. So make note. Hopefully you've already started talking to your partner and started planning out the presentation for next week, because now you've got less than a week until you need to submit the file. Today what we're going to be talking about is we're going to go through Chapter 8, Sections 6 through 8. And these are some of the quantitative calculations that I mentioned at the end of the recorded lecture that I posted for last week. I hope everybody got a chance to watch that YouTube video. Like I said I would, I kept it under half an hour. I just wanted to supplement some of the things that we'd talked about at the treatment plant, and we'll actually see a few more things today that will, I'll ask you to think back on things you saw at the treatment plant. So before we get into the lecture, are there any questions related to the announcements? Any questions at all? Okay. So here, this picture is a pretty significant fish kill that happened in a river in Arkansas. I think that they never did determine the cause of the fish kill, and it was just a couple of miles downstream from a location where lots of birds also died. So with the birds dying, this most likely isn't due to dissolved oxygen going too low in the river. It probably was some sort of a toxic material that was released into the environment. But if we get things wrong at the treatment plant, this potentially is the sort of result that we could get by discharging untreated wastewater into a receiving body that's already impaired. So we want to make sure that we're providing enough oxygen at the treatment plant so that the microorganisms that are consuming substrate don't take that oxygen from the environment once the wastewater is discharged. So this equation explains how you can calculate the mass of oxygen required each day when you have the oxygen demand coming from 3 sources. And I want to point these out individually. The first one is related to the amount of substrate that's being removed, where S naught is the initial inflow concentration of BOD. S is the effluent concentration of BOD, and so the difference between the two is just how much the BOD decreased. And so obviously if the BOD of the water went down, that's because it consumed some oxygen in the process, and you have to supply that oxygen in order for that process to occur. P sub x comma bio is related to the oxygen demand of the biomass. And what you'll remember is that in all of the calculations we've done so far, when we've done the mass balance related to oxygen, we've looked at the oxygen demand of the biomass. Now this third term is a little bit new, and all it accounts for is the oxygen demand related to nitrification. And what we remember is that during the nitrification process, oxygen is consumed in order to eventually turn the ammonia into nitrogen gas. In the example we're working tonight, this lengthy in-class exercise, we won't consider the nitrification. Depending on the residence time of the solids and the configuration of the reactor. Sometimes reactors aren't meant to remove nitrogen. You know, if there isn't an appreciable amount of nitrogen in the wastewater to begin with, then there's no need to remove it. And so this third term only applies if nitrogen is being removed from the wastewater. Now, not all wastewaters have the nutrients required for the microorganisms to grow. And the text makes the point that in a lot of industrial wastewaters there may be BOD, but there would be a shortage of nitrogen or phosphorus. And so in those rare instances, sometimes the nutrients have to be supplied. At the treatment plant last week, Mr. Kelly was talking about a small wastewater treatment plant down by Beach Fork. Does anybody remember what he said about what their problem was at this very small treatment plant near Beach Fork?
They were having too high nitrogen, or was that at their plant?
I think he was talking about his plant. The one down at Beach Fork, their problem was that the wastewater there was highly seasonal, where during the summer they get plenty of flow, but during the winter they get hardly any flow at all. I guess it receives water from the campground and a few maybe vacation homes. And so during the winter time they actually didn't have enough food to keep the plant running. There wasn't enough substrate in the wastewater, and so after consulting with the folks at the Huntington Sanitary Board, what they ultimately started doing is adding dog food to the treatment plant to provide the substrate. So that's just an illustration of how sometimes what you wouldn't expect, you know, a shortage of substrate or nutrients can cause operational difficulties. And so here, if we look back at the formula that we say represents a typical cell, you know, the biomass, the typical chemical concentration of biomass is here. On a mass basis, nitrogen accounts for 12% of cell weight. And so if cells are growing to remove dissolved BOD, we have to make sure that there's at least 15% of the mass that's being taken up available as nitrogen. So on a molar ratio, that's 5 to 1 approximately. And the same thing is true of phosphorus, except for that a much smaller quantity of phosphorus is required. Only about 1/5 of the mass of phosphorus is required compared to that of nitrogen. And so typically the rule of thumb is that if you have, for every 100 grams of BOD that's being removed, 5 grams of nitrogen and 1 gram of phosphorus, then that will be an excess of nutrients. And you'd rather have an excess of nutrients than a shortage, because if there's a shortage of nutrients, then the microorganisms aren't able to remove the BOD. And so you want to have just a little bit more nutrients available than they actually require. Now this varies based on solids retention time. This is for a solids retention time of greater than 7 days, and so that's kind of on the long end of things. But remember that when you change the solids retention time, that changes the food to microorganisms ratio, and when you're loading higher, when you're doing a high rate loading, then it may require even more nitrogen and phosphorus than this 5 to 1 per 100 grams of BOD.
When you give that extra, you got the extra nutrients in there. That's what promotes algae growth, right?
Yeah, and so, you know, if there's an excess, then that will go into the receiving body, and it will get into grow algae, and so you don't want to provide too much of an excess, just barely more than you would expect the microorganisms are going to require. Now, in most cases, and this is the case down in Huntington, they don't do anything to change their nitrogen-phosphorus balance. They already have an excess of nitrogen, in fact, quite a bit excess nitrogen, to the point where they were going through that cycling of sometimes they aerate, sometimes they don't aerate, to try and promote a little bit of nitrification, denitrification. It's not super effective because their plant wasn't initially designed for nitrogen removal, but they've been able to get a little bit of nitrogen removal just through this ad hoc aerobic, anaerobic cycling that they do. In the nitrogen removal process, it consumes alkalinity. And just to refresh your memory on what the definition of alkalinity is alkalinity is that chemical constituent that neutralizes acid. And so the two main components of alkalinity in water are carbonate and bicarbonate. And strictly speaking, hydroxide ion also neutralizes acid, but the concentration of hydroxide ion in water is very, very low, like 10 to the minus 7th when it's a neutral solution. And so usually your alkalinity is going to be in the form of carbonate and bicarbonate. And because nitrogen removal consumes alkalinity, you need to make sure that at the headworks of the treatment plant there's between 70 to 80 milligrams per liter of calcium carbonate if nitrogen, for typical nitrogen removal. For the typical amount of ammonia in the water, this is about how much alkalinity is required to buffer the solution, meaning that if you have less than this, then there's a risk that the pH will change through the treatment process. The pH would go lower because of the nitrification process. Okay, a few more odds and ends. We've talked about sludge volume index, SVI, and here in this figure it just illustrates the test that is used to characterize how easily sludge settles. And remember, if we take a step back from the wastewater treatment process and we ask what's the whole point of what's going on, we're trying to turn something that is soluble into something that will settle. The BOD that is dissolved in water, no matter how long we leave it in a tank, the dissolved BOD will never settle, because it's just like if you put salt into a glass of water and stir it. Once it's dissolved, it will only precipitate if you have a chemical reaction, or if you add more salt, eventually it'll reach the solubility limit. But in the case of BOD, once that BOD is dissolved, the only way you can get it to settle is by converting it into something else. And so what we do is we convert that dissolved BOD into the bodies of microorganisms. And we want those microorganisms to settle very easily, because when it gets into a clarifier, we want to be able to distinguish the effluent, the supernatant in the clarifier, the water that's at the top, the clear water we want to have as separate as possible from the solids that are settling. And so in a test like this, sludge volume index, SVI, is a way of characterizing what volume a gram of sludge will occupy after 30 minutes of settling. And so you look at the formula here. You measure the settled volume of the sludge after 30 minutes. And so this is showing what happens after 3 minutes, 10, 15. After 30 minutes, presumably it's occupying even less volume. And so you would have the settled volume of the sludge, and then the suspended solids that you start off with, and that gives you the sludge volume index. And just roughly speaking, if you have less than 100, then that means the sludge is settling very well, because it's not occupying too much volume after 30 minutes. But if it's settling so slowly that there's a really high volume in the settled sludge, in this graduated cylinder, if after 30 minutes the sludge is still, really high, then that's going to give you a big numerator that'll increase the SVI. And usually what causes really poor settling is the algae that's growing along with the bacteria. Filamentous algae. Filaments are long, skinny fibers. And if you have a lot of long, skinny fibers, then the sludge particles will actually adhere to those fibers, and then it sort of has a hard time settling, because those fibers are vertically oriented, and so what settles quickly is a sphere. Spheres settle quickly, whereas something that's long and sort of meandering, like a filament or a long piece of algae, if there is sludge particles that are stuck onto that, then it's not going to settle very well. And so that's why filamentous algae are considered kind of problematic, is because it interferes with the sludge's ability to settle. Now, to talk about the sludge volume index, remember that what this test is trying to simulate is what's going to happen to the wastewater when it gets into the clarifier. So the water leaves the aeration basin where there's lots of air being added to try and promote substrate removal. So it's lots of mixing here. It's a very vigorous environment. When we walked close to the edge at the treatment plant last week, it's sort of splashing a little bit. I stayed away from the edge because I didn't want to get the splashing on me. That's the aeration basin. But you can walk very close to the clarifier, and at the Huntington plant, the clarifier was where it had all those V-notched weirs, where it was long and the water was flowing over the edge, very calm, low flow rates, because we don't want to disturb the settling. And so there's a table I'll show you on the next page that shows the typical range of how big the surface area should be in order to get good settling performance. Because if you have a very small clarifier, then you're loading a lot of water into it over a relatively small area. If you look at overflow rate, it has the same units as velocity. Going back to fluid mechanics, let's take a look at the units of overflow rate. Q has units of cubic meters per second. Area has units of square meters. And so Q divided by A is going to have units of cubic meters per second, have square meters on the bottom, and so it's just meters per second. And so what this is equivalent to, the overflow rate, is equivalent to a velocity. And we want to have very low velocities so that settling isn't disturbed. And so what is good for settling is a big clarifier area. You want to have it really a wide, enormous tank. But that's bad for your pocketbook. It's too expensive to make the tank huge, large diameter tank. And so for economical purposes, you want to make the surface area as small as possible. And so it's this balance of you want to have good enough settling behavior, but you don't want the clarifier to be oversized. So this figure is taken from the text, and it mentions that clarifiers are typically sized according to two criteria. The first is the overflow rate, which we've just been talking about. That is the Q, the liquid loading rate, the water that's flowing through the reactor, and then A, which is the bottom cross-sectional area of the clarifier. And so this is showing it both in traditional units for the gallons per square foot per day, and here are the SI units, and then it's showing the average flow rates and the peak flow rates. The other consideration is the solids loading, because it's not just about the Q, the liquid flow rate, but also you have to ask how high is the concentration of solids, because if you had a very low concentration of solids, maybe they settle more easily than if it's a very thick, heavy sludge that will settle more slowly. And so both of those factors influence how big you want to make the clarifier. And in both of these cases, you'll notice that the denominator is units of square meters. And so it is cubic meters per day per square meter. And so like an average value for activated sludge, maybe it would be 20 cubic meters per day per square meter of area. And so for a clarifier, this is our little diagram of a clarifier here. If this was 1 square meter in area, what that loading rate says is you could have 20 cubic meters per day of water coming into the clarifier. But then the other way of looking at it is the mass of solids. And so a typical average solids loading rate might be 5 kilograms per hour for every square meter of surface area. So the mass that it's talking about isn't the mass of BOD, it's the mass of solids, the mixed liquor volatile suspended solids, which we give the variable X in our calculations. So those are the two different approaches, and what you would usually do is you'd calculate the area needed for both, and then you'd pick the larger of the two in order to be conservative. And so you'd know from your design what is the liquid loading rate, Q. You'd know from your design what's the solids loading rate based on the mixed liquor. And so that would give you two different required areas, and you pick the larger of the two, and then everything will be fine. Any questions about this table? All right. Now, in the treatment plant, it's critical that the dissolved oxygen stay high enough that the aerobic respiration can continue. There are anaerobic bacteria that will break down BOD, but they work very, very slowly in comparison to aerobic bacteria. And so if we have the DO below 1.5, then the problem there is that the rate of BOD breakdown will decrease because it will begin to favor the anaerobic microorganisms. So 1.5 milligrams per liter is a typical minimum value. And then the other issue with a low dissolved oxygen is that filamentous organisms can begin to grow, and they don't settle well. That's the problem. So here's in the final exam, maybe I would ask, what is the problem with filamentous organisms? And you'd have to remember that that's related to how well the sludge can settle. And so if there's a lot of filamentous organisms, then the sludge settling characteristics will be bad. Now, there's no dissolved oxygen that's too high, like it will begin to hurt performance. But what the text mentions is that if you go above 4 milligrams per liter, you're just wasting money. It doesn't speed up the process any faster to have dissolved oxygen above 4 milligrams per liter, but it sure costs a lot of additional electricity, and you have to have more blowers, more aerators, diffusers. Everything has to be used more in order to get the dissolved oxygen higher. So between 1.5 and 4 is the typical value. Another thing, during the operation of activated sludge, one of the things that the operators are keeping track of is how much sludge should be wasted. And you'll remember when we were in the lab, he had on his whiteboard a calculation that was saying what is the concentration X of mixed liquor volatile suspended solids. And the way that that is controlled, the way that you control the concentration of solids in the aeration basin is how much of the waste is recirculated versus how much of the waste sludge is sent to a tanker truck in their case. They used to incinerate the sludge, but now they send it to the landfill. And so it's by controlling how much sludge is landfilled that the concentration of solids in the aeration basin are governed. And one of the things that he talked about in the tour was in the clarifier, the thickness of the sludge layer may vary quite a bit from time to time. Sometimes when they haven't, in the snowy months, when it's difficult for the trucks to get out to the treatment plant, they maybe won't stop by for several days, and they'll start accumulating sludge in their holding tank, accumulating sludge in the clarifier. And so if they get too much sludge in the clarifier, then there's not enough depth for the actual settling to occur. You know, there's a storage layer and a settling layer, and if you store too much sludge, then it can interfere with how well the liquid is settling. Okay, so we've talked about waste-activated sludge as well. So here's a diagram that's just refreshing our memory of what's happening here. The water that comes into secondary treatment is coming off the top of the primary clarifier. And so it's already had some removal of the suspended solids. It hasn't had any removal in dissolved BOD, though, because the dissolved BOD can only be removed by microbial action. And that's what's happening in the aeration tank. The volumetric flow rate Q is just whatever flow is happening at the treatment plant. But it's being joined by the sludge. And this Q sub R, the recirculated volume of the sludge, typical sludge pumping rates are between half to 75% of Q. And so he was saying that anybody remember what the flow rate was the day we were there?
12?
I think it was, in the neighborhood of 10 MGD, 10 million gallons per day. So if you have 10 million gallons per day going through the treatment plant, that means that between 50 and 75%, you may have 5 million gallons per day is the flow rate of the sludge. And so it would be pretty easy to size the aeration tank just based on the flow rate of the liquid. But remember, there's also this recirculated flow rate of the sludge that's going through as well. The clarifier, the concentration of this X sub R, that's the concentration of the solids that's coming from the bottom of the clarifier. It can go between 4,000 and 12,000, and the kind of ballpark value of solids in the aeration tank is maybe around 2,000 milligrams per liter. They will increase when they're sizing the pumps that, the pipelines and the pumps that recirculate sludge. Even though the typical value is maybe 50 to 75% of the liquid flow rate, they'll make sure that those lines can carry even more than that, because sometimes when the concentration of solids is low, like after a wet weather event, they have to recirculate even more than they usually do. And so you have to build flexibility into the treatment plant so that maybe the sludge pumping rate would be as low as 50% and as high as 150% of the liquid's flow rate. Now here's the clarifier, and you'll see that I've marked here something called the sludge storage zone. And that's because the particles are settling downward and the water is flowing over the top of the clarifier through the weir. And so there's going to be some layer here of the sludge accumulating. It's not always completely clean down the edges. Actually, the sludge settles better when it's sort of packing, and it goes through a process called zone settling. And so it has to, in deciding how big the clarifier is going to be, there should be some of the volume that's for active settling and some of the volume that is dedicated for the storage of sludge solids. Now we can calculate the ratio of the recycle flow rate versus the liquid flow rate going through the whole system. It's the ratio of 1 minus the hydraulic detention time divided by the solids retention time. The solids retention time is always going to be equal to or usually greater than the hydraulic detention time. And you can see it also takes into account the ratio of the solids concentration in the recycle and the solids concentration in the aeration basin. So it's from this relationship and the mass balance that goes into it. This is just the solids flowing in minus the solids flowing out, and we set it equal to 0 because we say that there's no accumulation in steady state. We don't want solids to be building up inside of our control volume. And so this is how we can calculate the solids retention time. How long does a particle, the average particle that's being recirculated around, how long does a solids particle spend in the reactor? And so you can see that's related to the volume of the aeration basin, the concentration of solids inside of the aeration tank, and then the waste flow rate and the concentration of solids in the recycle line. So you control the solids retention time through this wasting rate. And X sub R is controlled indirectly by the wasting rate and also by how well your clarifier is able to settle out particles. Hopefully it captures all of them. So sludge wasting is one of the few, levers that the operator can pull on to try and guide the performance of the treatment plant once it's been built. There's a lot of things that you only get one chance to get it right. During the design phase, when you're sizing a big concrete aeration basin, if you make it too small, it can be millions and millions of dollars to fix that mistake. And so some things you have to get it right the first time, and there's really a limited opportunity to correct it. But the sludge wasting rate is the one thing that the operators can adjust on a daily basis once they've done analysis of the concentration of solids in the aeration basin. And so there would be a valve coming out of the clarifier, and it's going to send the settled sludge one of two directions. It will send some of the sludge for recycle, some of the sludge will go to wasting. And it may not be continuous. It might be that they suck out some of the sludge solids over a short period of time and then send those for disposal. But over the long run, the average waste rate is governed by the solids retention time, the solids concentration in the recycle volume, and X, the solids concentration inside the aeration tank. Okay, so what we're going to go through now, it's probably like the next, I don't know, 8 or 9 slides, is we're going to look at different configurations of reactors and see what makes them unique. And this is very important that you learn each of these. There's more in the book. The book actually has, I think, between 20 and 30 reactor configurations, and I'm not going to ask you to memorize all of that. But I would like you to conceptually understand how the different configurations change the effluent quality and why we change things around sometimes, like what we're looking for. And so this is the baseline, the completely mixed activated sludge. This is what they have in Huntington. It's just the standard reactor. In a standard reactor like this, the water's coming from the primary clarifier into the aeration basin, mixed with activated sludge. It settles. Some of the sludge is wasted. The water off the top, the clear effluent, is sent for disinfection and ultimately disposed in the stream. So here are the parameters that describe the performance of this standard completely mixed activated sludge. Solids retention time between 3 and 15 days. You can see the food to microorganisms ratio, mixed liquors, suspended solids, typical concentrations there. The advantage of this is that it's so common that its performance is really well known. This is the most proven design in activated sludge treatment, and so it's easy to find operators who've got experience with it. And because you've got a big volume in the aeration tank, and because the incoming flow is mixed in the aeration tank, it sort of can handle shock loads. What do you think shock loads are? Any guess on what that phrase means, shock loads? It doesn't have anything to do with electricity. Right. If for some reason suddenly there's a big concentration of BOD, maybe connected to your network is a food processing plant, and once per week they clean a tank of some sort. Maybe at the food processing plant, all of the yeast and bread scraps go to the bottom of a tank, and then once per week they clean it out, and so suddenly there's a big rush of BOD. In a reactor like this, because you have a big aeration tank, all of a sudden that big inflow of BOD is going to be cushioned a little bit because you've got such a large volume in the aeration tank. There are other reactor types we'll look at in a minute that can't handle that same kind of shock load because they've got a small aeration basin, or because they're not even complete mix, because some of those reactors that we're going to look at are configured as a plug flow reactor. So that's one of the big important advantages of having a large aeration basin, is the ability to sort of even out the shock loads, and because of that it has uniform oxygen demand, meaning that you're not going to have huge swings in the amount of oxygen that has to be supplied. Now, the problem with this is that it is susceptible to the growth of algae that are going to cause problematic settling of the sludge because of the long retention time. a solids retention time of greater than 5 days, because this goes, all the way up to 15 days, longer retention times are going to promote the potential growth of filamentous organisms. Okay, so this is sort of the baseline against which everything else is compared, because this is the most common. Now, here is high rate aeration. And in high rate aeration, if you look at the aeration basin, it's configured a little bit different. So what do you see is the difference between complete mix and high rate aeration? Right, so you're seeing that there's different chambers here, and so this is a plug flow reactor.
Is this where the oxygen being introduced so the water spirals all the way through?
Well, it can be, but not necessarily. The distinguishing factor here is just that the water that comes into the reactor is kept together, and the water that's exiting the reactor is kept together and separate. And so the advantage here is it's in the kinetics. Let me remind you what first order kinetics are. First order kinetics say that the rate of the reaction depends on the concentration of the reactant. Okay, so in our first order kinetics, the typical graph looks like this. So here is the time, and here's concentration. And in first order kinetics, the concentration is going down very fast to begin with. This is a steep slope here because at first you have a high concentration, and so the bugs are eating quickly. But then as the concentration goes down, the bugs are eating more slowly because the rate of the reaction depends on the concentration of the reactants. So from our standpoint, from an engineering standpoint, what you want is you want the bugs to eat, and you want them to eat quickly. The problem here is that as soon as the high strength waste comes in, it's spread out everywhere. So as soon as the substrate comes in, it's mixed so that the concentration of the aeration basin is low. And so the rate of the reaction is going to be slow. But here, at the beginning of the plug flow reactor, the concentration of BOD is very high. And so what that means is that the rate of the reaction will be high at the beginning of the reactor. And so it's more efficient. You're getting more bang for your buck because in the early stages of a plug flow reactor where the concentration is high, so is the rate of removal. And so for a volume by volume basis, a plug flow reactor is always going to get more removal than a completely mixed flow reactor. So that's the advantage here. The advantage that's listed is there's less aeration volume required. And that's because of the kinetics that are associated with first order reactions. And so the aeration volume is smaller. You don't have to have as big of a basin, and therefore you're not using as much oxygen because you don't need as much oxygen towards the end here. They may have the first chamber aerated high and have the middle chamber aerated medium and the last chamber aerated low because the bugs aren't using that much oxygen towards the end, so you don't need to provide as much oxygen for them. Now, this is less stable. Think about a shock loading. The advantage in this reactor was that if you have suddenly a high concentration of waste come in, it's cushioned by the fact that you've got one big tank that's being mixed. In this case, a shock loading is going to stay together. Instead of being mixed out and sort of spreading out the problem of a shock loading is staying together, and so If you have too much BOD suddenly, the bacteria can be overwhelmed, and that will continue as that element of water travels through the reactor. So that makes them less stable, how threatened they are to shock loading. The effluent can be lower quality, potentially, if they're short-circuiting in the reactor. And here, high-rate aeration means that, look at the solids retention time. It's very low. And our F to M, food to microorganisms, is high. And so let's compare these values. I bolded this one because it's especially important. Let's look back at the table on the previous slide. It said, typical solids retention time, 3 to 15 days. That's how long the bug is going to spend in here going through the cycle until finally the sludge is wasted. On average, between 3 and 15 days in the standard completely mixed flow reactor. And the F to M, 0.2 to 0.6. So now look at this. Much higher F to M. Lots of food, not very many microorganisms. And the reason why is if you look at the solids retention time, the solids retention time is low. The bugs aren't spending that much time in the cycle before they're wasted. And so that's another reason why the effluent quality isn't as good, is that we're trying to load as much BOD through the reactor as we can. You're going to have a high volume of sludge, and because the solids retention time is so low, you can't get nitrification. Nitrification requires long solids retention time. And then the other issue is that because the volume of the reactor is so small, then you can wash out the microorganisms inside the reactor during peak flows, like during a storm event. When you have a really high flow rate, there's just not enough bugs that will stay in the clarifier and being recirculated through. And so you can lose potentially your secondary treatment during a rain event. Okay, so the main thing, if you boil it down to one big difference, it's the solids retention time. 3 to 15 days versus less than 1 day, maybe 1 to 2 days for high rate aeration. So high rate, that's talking about the rate that BOD is being loaded. The high rate refers to the F to M ratio. Lots of food, not as many microorganisms. High loading rate, high mass loading rate. All right, so here's a little bit more complicated conventional extended aeration. Now this is the opposite of high rate aeration. High rate meant that we're going to have a short retention time and really a lot of food per microorganism. This is the opposite end of the spectrum. Now we have very low F to M and very long solids retention time. So this is great for nitrification. You can have really mature nitrifying organisms with a solids retention time this long. So that's what it means by high quality effluent, is because you have such a high solids retention time, not only is it removing BOD, but nutrients can be removed as well. You have to have a large aeration tank, which is expensive, but then the advantage of that is that you're kind of immune against shock loads. The bigger the aeration basin, it's acting as sort of a built-in flow equalization basin. And so it can treat shock loads because it's so large. But then if you have a large aeration tank, you're having to add air to all of that volume, so it's going to be costly, high energy requirements because of that expensive aeration that's required. This is usually used where the flow rate is relatively small, because to use extended aeration for a big city, you'd just have to have an aeration tank that's so large it wouldn't be practical. So smaller towns are the ones that would usually have extended aeration. So I'll give you a glimpse at the final exam. On the final exam, maybe I'd ask you, why is this called high rate aeration? It's not because they're adding a lot of air. The high rate is talking about the mass loading rate. Okay, so another glimpse of potential final exam questions would be here, why is this called extended aeration? Extended, what is that referring to? And what it's referring to is the long solids retention time. 20 to 30 days is exceptionally long. Okay, now we get into some more exotic configurations. You can see here it's extended aeration again, same as the previous slide. This is extended aeration, and so is this. But in the oxidation ditch, instead of just being a big tank where it's all being mixed together, this is trying to combine plug flow reactor and completely mixed flow reactor. So the water is going around in a circle, but the reason why you have it going through this racetrack circuit is that different things will happen at different parts of the reactor. Right here, when the inflowing water has a high BOD, in this zone, there's going to be a lot of BOD. It's aerated. But as the water flows in this direction, the BOD is being consumed. And so different populations of microorganisms can set up in different part of the reactor so that you can have nutrient removal in one section of the reactor, and maybe they won't oxygenate the entire ditch the same amount. They might put aerators only in certain locations here to try and remove nutrients a little bit more effectively. So nutrient removal is possible. This bullet point here is unique because of the fact that it's going around in circles and the flow is isolated at different zones. You have the high concentration of BOD to begin with, but and in this zone, the nutrient removal microorganisms aren't going to be able to compete. But in other zones, they might be able to compete. You're setting up a different environment that favors a variety of microorganisms instead of just having it all mixed up together like you'd have in a conventional aeration tank. This requires a lot of space to have an oxidation ditch, a big surface area, requires more aeration, and so the benefits are there because of nutrient removal, but then there's additional costs as well. Okay. In Charleston, they're starting to experiment with adding high-purity oxygen for aeration. And here is a diagram that shows one way of doing that. And we're looking at the cross-sectional view here. This is different from most of the aeration basins we've looked at before because here there's a roof on the aeration basin. All the other aeration basins have been open to the atmosphere. Here, look at this one. It's open to the atmosphere. This little triangle here and then the dash marks, those represent ripples. That is kind of indicating that the air above the aeration tank is just atmospheric oxygen, and that's different from the high purity oxygen. Here in the high purity oxygen, what they're doing is, whether it's being generated on-site or off-site, they're putting a high concentration of oxygen into the headspace above the water, and then in this case it's showing a mechanical mixer is spinning to agitate the wastewater and also to get the high purity oxygen down into the wastewater. Now, the advantage of this is that you can have a very good quality settling sludge. And so having that good oxygen there is going to promote the growth of bacteria and discourage the growth of filamentous organisms. But it's like you can never win everything because you have poor nitrification, because remember, nitrification occurs in the absence of oxygen. The nitrification-denitrification cycle has to have an anaerobic component to it. So this is good for moving BOD, bad for moving nutrients. And then the other problem is that it's a lot more complicated to maintain if you're having it sealed to the air. Because if there's a leak, if the oxygen is leaking out of the headspace there, number one, it's dangerous because oxygen can cause explosions and fires, high purity oxygen. But then the other issue is if you have a crack and that oxygen is seeping out, then that's just wasted the energy that's required to purify the oxygen, and then it slows down the reaction inside of the wastewater as well. So there's just more maintenance in trying to maintain an airtight chamber for the aeration to occur. Okay, here is showing a conventional plug flow reactor. This is different from the extended aeration plug flow reactor that we were looking at before. These are pretty common, and you can remove ammonia by having the different zones where maybe aeration would occur in one location, but then there would be, you'd allow it to go anoxic in certain zones. And that's what it's talking here about. Tapered aeration design is complex. To have a gradually decreasing concentration of dissolved oxygen is hard to get it right because the flow rates are always changing through the day and over the week. There's seasonal cycles in flow rates, and so the operator is constantly having to adjust how much oxygen is being added to match the liquid flow rate if you do want to try and remove nutrients in this. We'll just look at a couple more of these before we get into the in-class exercise. Now, this is plug flow, same as the previous slide, but look, there's a critical difference. In this first plug flow, the conventional plug flow, the wastewater only comes in one location. It comes in at the beginning of the reactor, and then the water flows until it gets to the outlet. In a step feed, you see here it says step feed. What's different in this configuration is that the wastewater comes in at more than one location. And so does the return activated sludge. The return activated sludge is being added to the tank at a different location. And so in order to spread things out, you're sort of distributing where the incoming wastewater enters the tank. And then the advantage of doing something like this is you're spreading out the load, and so you have a more uniform oxygen demand. One of the challenges here, remember, was you have so much oxygen demand at the beginning, and at the end, very little oxygen demand. And so if you have step feed, if you're feeding the substrate at lots of different points in the plug flow reactor, then that spreads out where the oxygen is needed. So it kind of simplifies the operation a little bit. It makes it more flexible. But it is complicated to make sure that the wastewater gets at different places. And last week when we were on the tour, Mr. Kelly alluded to that. He said that at their plant, they're doing a variation of this. They have the aeration basins like this, and the water is coming in, and they have gates, several different gates. And what he was saying is they're trying to get the water to come at the same flow rate through each of the gates. And so this first gate is open just a little bit, and then they have to open each gate more and more, and then at the last one, it's open all the way. Because if the water is coming from this direction and they're open the same amount, then naturally there would be very little flow coming out at the end, and most of the flow would be at the first gate. And so it can be operationally complex to try and spread out the flows to make sure that the same amount comes into the aeration tank at every location. So it's difficult to split those flows accurately. All right. Here, in this contact stabilization, the theory here is that instead of just immediately returning the sludge into the aeration basin and putting it in contact with the incoming water, in the stabilization area, you're sort of aerating and mixing the sludge, but it's not yet in contact with the BOD. And doing that makes it so that the sludge settles better and it reduces the sludge volume. You still have the aerobic removal of BOD here, but the stabilization what's being stabilized there is the sludge. And so it's a little bit more complicated to make sure that the return activated sludge doesn't spend too long in the stabilization basin, because if the sludge is in the stabilization for too long, then they'll starve because there's no new BOD being added in the stabilization basin. The BOD is being added in the contact chamber. The other thing here is it's not going to remove nitrogen because there's no part of this reaction that there is a lack of oxygen, and you have to have some sections that are anaerobic for nitrogen removal. But you get a good quality sludge out of that. And then I think this is maybe the last one. Oh no, we've got a few more. This is, you can see two different aeration basins. One is the aeration basin for the removal of BOD. Another is specifically for the nitrification, denitrification. And so in the nitrification tank, one of the big problems with the nitrogen removal cycle is that those microorganisms get outcompeted by just the typical carbon-consuming bacteria. And in the recorded lecture, I talked about the idea of selectors, and that a selector is a very small tank before the main aeration tank to try and create a favorable environment for bacteria. And that's what this essentially does in a two-sludge system, is you have different environments for different ecosystems, and those two different environments give you a better variety in the nutrients that are removed, and it can also keep the toxic environmental contaminants away from the more sensitive nitrogen removers, because the microorganisms that consume BOD, they're relatively strong, and a toxic inflow like a pesticide or fertilizers that maybe would cause problems for these weaker nitrifiers, the BOD consuming microorganisms can handle them just fine. And so it's like you're cushioning in the aeration basin. It's sort of equalizing the flow and getting rid of the shock loads. But obviously having two separate systems like this is going to increase the cost of the system. It's going to make it a lot more costly. This orbital is a proprietary system that is kind of like an oxidation ditch. You'll notice that the water is going around in circles. It's a racetrack configuration. And so the outer ring is a plug-flow reactor that's anoxic. And then the water exits that outer ring and flows into chambers that are now aerobic. And so inside of each ring, there's pretty good mixing inside each ring as the water goes around. But by keeping it separate, you have the advantage of a plug-flow reactor. And so the different amount of air is going to be added in each of the different rings as the concentration of BOD goes down. And so you can save aeration by having a high concentration of BOD to begin with and decreasing concentrations. And in the anoxic ring, you'll have the removal of nutrients. And here's another way of doing the same thing. Schematically, here you're trying to have some of the water be anaerobic and some of it be aerobic. So in this, the water is moving around, and where you're injecting the oxygen stays fixed. It's in one location and it's not moving. This is the opposite. This arm swings around inside of the tank, and this is where the aeration happens. And so as this goes through in circles, you're going to be oxygenating this part of the reactor now, but then as it rotates, part of the reactor is going to be losing access to oxygen. The advantage of this is that you can have the removal of nutrients because you have some zone that will be anaerobic and some of the zone will be aerobic. You're going to have low biosolids production because if you look at the solids retention time, it's very high, and meaning that you have a very low food to microorganisms ratio. And so that will cause endogenous respiration to break down the sludge. The microorganisms in here are going to be eating one another, and their cellular respiration is going to be causing them to basically lose weight, and it gives you less sludge that has to be disposed of. And sequencing batch reactors was included in the recorded lecture that was posted online last week. The advantage of a sequencing batch reactor is that you don't have to have a separate clarifier. And so, this isn't 4 different tanks. This is just one tank that's going through 4 cycles. There would be a period of time when the tank is filling up. Then there's the reaction phase where you're injecting oxygen and the BOD is being broken down. And then you stop everything and it's perfectly quiescent inside of the tank, which makes for very good settling. And then once the sludge is accumulated at the bottom, then the effluent is taken from the top and this sludge can be disposed of. And so sequencing batch reactors have very good quality of effluent, and the volumes don't have to be as big because you're combining both the clarifier and the aeration basin. But it's complicated because you have to have several tanks, and the water has to go somewhere all the time, and so you're constantly filling one tank while another tank is draining, and maybe a third tank is going through the aeration basin, going through the aeration process. And so in order to get a sequencing batch reactor to work, there have to be several different parallel reactions occurring at different phases. Because of that, a big peak flow due to a rain event can be disruptive to the process if you've got a nice settled scheme where you're in a pattern and then suddenly there's lots more water coming in than normal, then that can throw off the process. This system is known as ICEUS, and it gets its name Intermittent Cycle Extended Aeration System, and so that's pronounced ICEUS. And ICEUS is a hybrid between a plug-flow reactor and a batch reactor. And so what makes it a plug-flow reactor is the fact that water comes in on one end and it exits on the other. And the way that water is exiting is there's like a little float on top of the water, and at the top here is where it's the opposite of the direction from where the solids are settling, because here in the main chamber the settling is going down. You can see the particles will go down, and so the water at the top is the cleanest, and so you're sucking water off the top of this clarifier, and so the effluent has a very good quality. But then at the same time as that, it's a sequencing batch reactor, meaning that the overall liquid level can be going up and going down, and so during the sequence of filling and emptying, you're also having continuous inflows. And so you'll notice there's no sludge removal that's shown on this diagram. It's at the end of the reaction when the liquid level is very low that then the water at the bottom of the tank would be evacuated and the sludge would be disposed of. And so it's 2 simultaneous things. It's the sequencing batch reactor of part of the time it's filling, part of the time it's aerating. Well, during the settling and decanting phase is when the effluent would be removed from this batch reactor. All right, so we've been at it for an hour. Let's take a 5-minute break, and then when we get back from that, I'm going to give you this in-class exercise 11, which I'm going to ask you to work on with your partner for next week's presentations. Here's a picture of a lake in Bolivia. I think it's Bolivia. And what we're looking at is not a bunch of swirling mountains in the middle of the lake, but rather this lake is eutrophic, meaning that there's so many nutrients in the lake that algae are really growing out of control. And so the wind blows and sort of gets the algae together, and you can see the currents over time have sort of put a swirling vortex of algae through that lake. And this is one of the consequences of excessive nutrient deposits into a water body. Now, when we were talking about nitrogen removal, remember that you can either have the nitrification, denitrification occurring in different reactors, or it's possible with the granular media to have aerobic microorganisms living on the outside that do the conversion of ammonia to nitrite and nitrate. And then on the interior of a granule where conditions are anoxic, meaning that there's not enough oxygen for the aerobic bacteria to grow, anaerobic bacteria can take nitrate and turn it directly into nitrogen gas. And so if you are able to configure a reactor that promotes growth of granules like this, then that can be really beneficial for nitrogen removal. So we'll just take a look at a couple of the configurations, and these schematic diagrams are just meant to help you understand what some of the consequences are of configuring a reactor in a certain order. And so here, when you have a large aerobic basin followed by a relatively smaller anoxic basin, the purpose of the anoxic basin, remember, is to convert the nitrate into nitrogen gas. And so that reaction always occurs only in the absence of oxygen. And the endogenous respiration that this is talking about is reminding you that here in this section of the reactor, the bacteria are actually using their own body mass as the energy source, and they're using the nitrate as an electron acceptor rather than as a food source. Now this reactor, the Lutzek-Ettinger reactor, switches those two, because previously we had aerobic and then anoxic. So here you're switching the two. You've got the aerobic reactor first, and then the anoxic reactor where there's not enough oxygen, and then the second one is aerobic. Having the anoxic basin first, the advantage here is that you're giving those microorganisms the first opportunity to use the BOD. Because ordinarily, microorganisms that remove nutrients are relatively slow and weak, and so this is a selector that favors them instead of favoring the microorganisms that remove carbonaceous materials more quickly. And so you can see that there is a feed of nitrate going from the aerobic reactor to turn the nitrate into nitrogen gas, and there's also the return of sludge into the influent. But the main thing for you to look at here is, why would we have anoxic first? It's going to speed up the reaction compared to a post-anoxic. So this is called post-anoxic, meaning that the anoxic zone is after aerobic. By contrast, this is pre-anoxic. Pre-anoxic is going to be quicker because the substrate concentration is higher. And now this is modified because the internal recycle goes into the influent where it's going to be mixing with the sludge, compared to the internal recycle going directly to the anoxic. It feeds more nitrate than ordinarily would occur in the normal Lutzek-Ettinger. This is the modified Lutzek-Ettinger. It's just a variation in how much of the flow comes from the aerobic basin into the anoxic basin. And this can yield very good nitrogen removal. The effluent from here is 4 to 7 milligrams per liter, which is a lot lower than what they're achieving in Huntington, where they're, on a good day, getting maybe 25 milligrams per liter of nitrogen in their effluent. And that's even with the cycling of aerobic and anaerobic that they're already having. We've already talked about step feed today and the benefits of step feed. So step feed is where, instead of only having one place, the inflow coming in, it's coming in at several different locations in the plug flow reactor. The benefit here is that you're going to have more of these zones where the rate of the reaction is high. Because remember, in plug flow reactor with first order kinetics, the rate of the reaction is highest when the concentration is high. And so you're getting more efficiency when you have step feed. And so this is taking the plug flow reactor, which is good from kinetics, step feeding, which is good for kinetics, and it's also combining pre-anoxic on top of it. So this is really the best of so many different worlds, where pre-anoxic, remember, creates an environment that's favorable to those weaker organisms that ordinarily would get outcompeted if they didn't have first access to the substrate. And so they're getting the fresh incoming BOD before the aerobic microorganisms. And so this improves the reaction performance, and the size has to be smaller than it otherwise would be. It's getting pretty complicated now. We already looked at a two-sludge reactor earlier in today's lecture, but when it comes to a two-stage reactor where you're specifically going for nitrogen removal, sometimes you have to add methanol. You have to add an external carbon source for the nitrogen removal, for the denitrification. And so that's the unique thing for this nitrogen removal process that may not be present in a typical return activated sludge system. The nitrogen concentrations are going to be very, very low here, but it comes at the cost of an additional chemical constituent that has to be kept track of. It's going to increase the expense, and so remember the oxidation ditch from earlier today, and the oxidation ditch is where the water is flowing in a cycle over and over again, and it has the benefits of different zones of high substrate concentration close to where the influent is coming in, but then the aerators are not continuous. In this conceptual diagram, it's showing 3 aerators, and so immediately downstream of the aerator, there's enough oxygen that this zone would be aerobic, but as you get further and further away from the aerator, the dissolved oxygen concentration is going down, and finally, when the dissolved oxygen is exhausted, that's where nitrogen removal is going to occur. And so the anaerobic zone would be right before the next aerator occurs. What makes this resistant to load variation, the shock loading, is the fact that the oxidation ditch has a relatively high volume. It's big. Here's another picture that's showing the disadvantages of excessive nutrients. And obviously, people aren't going to be swimming in that lake. That's a lake. Yeah, very nice, right? All right. So here are some of the enhanced biological phosphorus removal techniques that the book talks about. Again, we've got anaerobic followed by aerobic. And so in the previous, when we were talking about nitrogen removal, we called this pre-anoxic. But there's a difference between anoxic and anaerobic. Anaerobic means absolutely no oxygen. Anoxic means a shortage of oxygen. And so for the removal of phosphorus, we have to be even more strict about how little oxygen there can be. And when we were talking about the concepts related to phosphorus removal, I introduced the 2 different kinds of phosphorus blends that is cycling between the orthophosphate and polyphosphate, where the orthophosphate is the easily dissolved form of phosphorus, and polyphosphate is what is complexed inside of the body of microorganisms. And so refer back to your notes about orthophosphate and polyphosphate. The challenge with a reactor like this, with a upstream anaerobic process, is that if you have the water in the anaerobic process for too long, then they can start to release the phosphorus that you're trying to get them to absorb in the aerobic zone. Having the recirculation of the sludge solids means that in the anaerobic zone, the microorganisms are becoming stressed and they think that they're on the verge of extinction. But when they get into the aerobic basin, those phosphorus accumulating organisms then will take up more phosphorus than they lost in the anaerobic stage of the reactor. And so you only want them in the anaerobic zone between 30 minutes to an hour. Any longer than that, and they can actually release too much phosphorus so that they won't be able to take up that much in the aerobic section of the reactor. Okay, so here is a three-phase process where we have anaerobic, which is strictly no oxygen, anoxic, which is a shortage of oxygen but not none, and then the aerobic aerated basin. And this staged process, gradually increasing the oxygen concentration, like it has in previous slides, we've been talking about selectors, where we're just trying to create a special environment for a unique strain of microorganisms that otherwise wouldn't be able to compete. And so in the anaerobic zone, you're removing phosphorus. In the anoxic zone, you can remove nitrogen. And then in the aerobic section of the basin is the removal of carbonaceous BOD. And so in one continuous reactor, just by varying the amount of oxygen that's available, you can have the removal of both nutrients and also BOD. So this is a complete process. Now the challenge here is that when wastewater flow rates are varying, it can be difficult to match, exactly fine-tune the amount of oxygen in the aerobic and the anoxic, and then you can't really change the size of the anaerobic basin, because remember, anaerobic means no oxygen. And so if your flow rate suddenly increases, what you would want is you want the anaerobic basin to get bigger, but you can't make the anaerobic basin bigger, not on the fly. And so what they maybe would do is they would have the diffusers across the whole bottom of it, and then they would just selectively turn these diffusers off, and if the flow rate increases, then they would increase the number of diffusers that they switch into the off position. So that would effectively make more of this reactor anaerobic. So they would have to really govern the amount of oxygen that's delivered in a sophisticated way. And computer controls and a lot of sensors inside of these different sections would be pretty important to getting accurate control of oxygen. Okay, so now we have several cycles, a second anoxic zone, and having that second anoxic zone after the aerobic zone allows for denitrification. Remember, denitrification is what we call the conversion of nitrate into nitrogen gas. And so we're not relying only on the recycle to have denitrification. And so anaerobic zone is removal of phosphorus. Anoxic zone is going to allow for some of the removal of nitrogen through the conversion of nitrate to nitrogen gas. But the second anoxic is more complete removal, and then you finally would have like a polishing stage. This last small section of an aerobic basin essentially is going to allow for the stripping of any any nitrogen that would be dissolved in the nitrogen that would be dissolved in solution, because you don't want those gas bubbles to start coming out of solution in the clarifier, because then they can suspend the sludge. Okay, that is it for tonight. Let's just take a final look at some of these announcements. The big thing that's on your plate is that the presentations are next week. I would encourage you to meet with your partner between tonight and next week. It's not going to be a very good presentation if you don't practice it. If you both prepare your own thing and don't get together to coordinate in advance, then it's not going to be as good a presentation as if you'd just gotten together and go over transitions and make sure that you both have pictures and that you've got your calculation example together. So between the 4 groups that we've got for next week, that's going to be between about 80 to 100 minutes. And so I'll have a brief lecture that I'll present after you do your presentations. We'll probably take, same as tonight, the majority of the class time. And then looking further into the future, I'll give you the next homework assignment next week in class. So we've only actually got the presentations that you're doing. That will be graded. There will be homework 4, which I'm going to give you next time, and then the the research papers that you're working on. And the research papers, I believe I said those are due on, the last day of class, April 29th. Okay, so that's it. I hope you have a great night, and I will see you next week for the presentations.